Okay, good morning everyone. So in last week we have already mentioned that how we are going to organize in this class, and then the several different teaching activities, and then the several the arrangement for this class, and also we start to review the semiconductor. And last week we mainly talk about the future outlook, that what will be the next big driving force that push us to further have the semiconductor innovation. And nowadays, today in today's class, we will back to the old history to understand that how semiconductor has been developing since several decades ago till so far. Of course, there are so many important innovations, but I think it's worth to find out that what would be the 10 most important innovations. So this is the slide I borrowed from the Dr. Maurice Chan, who is the founder of TSMC. He lists the 10 most semiconductor innovation based on his experience and his the careers. So the first one, which is the most important innovation, is happened in the 1948, which is a transistor. So since 1948, from the Shockley, Bardim, and these guys from the Bell Lab, they start to develop the transistor, that we have the kind of the device and architecture that help us to do the certain electrical switching. So that's first milestone for the whole semiconductor history. And then the second very important innovation is that we start to use the silicon, because of the silicon is a very good material that also is very easily accessible. So in later, from 1954, we start to switch. In the beginning, the first demonstration was on the germanium, but later we switched to the silicon, this kind of material. And nowadays, since 1945 until right now, that it's no doubt that the silicon is still the dominating material for the, I would say, more than 80% of application. We still need use a silicon-based material. So that's a beginning from the 1954, and then later from the 1958, which is another important breakthrough, is that we start to have the concept of the IC, which is an integrated circuit. So that's mainly developed by the first demonstration is demonstrated by the Jack Kilby from the Texas Instrument. And actually, that if you try to look at the biography from the Dr. Maurice Chan, that he also has mentioned that he was working with Jack Kilby at that moment. So that was a very interesting history. So he was exactly born and exactly work in the same kind of moment that the whole semiconductor technology is being developed. So that's starting from 1958, we have the concept called the integrated circuit. And another very important milestone is that since 1965, we start have the concept, what we call the Moore's law. So at 1955, that was mainly from the Dr. Golden Moore, but at that moment was in the company called the Fairchild Semiconductor, but later he became the founder of the Intel. So in the 1965, he proposed this kind of what we generally call as the Moore's law. Is actually as a empirical observation that the density of the transistor will be double every 2 years. So that's in the beginning it was just based on his previous experience, but later it's become the golden rule of the semiconductor, especially not only for the technology perspective, but also for the economic perspective, that's actually important to understand what would be the future of the transistor based on the Moore's law. And later, from the 1964, and then we start to have another very important breakthrough. That's what we call the MOS technology. So of course, right now I think the MOSFET, which is if you start in the semiconductor industry, or you start to follow some semiconductor basic courses, for sure the MOSFET, which is the most important device architecture. Actually, in this class, we also will use a lot of the MOSFET as an example that everyone can understand what would be the reliability issue in the MOSFET. But that actually is not the first transistor. First transistor was demonstrated by using the bipolar junction transistor, and later we have this MOS technology, where we have the MOSFET and we have a silicon dioxide as a gate. And we also have what we call the CMOS. So CMOS is what we call the complementary MOS technology, where we both have NMOS and PMOS at the same time, and that's become the building block for the digital circuit application. So that was all happening from the 1964 till 1970. And afterwards, there's also a very important technology start to getting more and more mature, which is memory. So in the case of memory, that at the moment is mainly focused on the DRAM and also the flash memory. So there are several key people at the moment to focus on DRAM and flash, and then for sure the one that we have to definitely mention is the Simon C, which is previously as the professor, the distinguished professor in the NYCU, NCTU, but now he has been passed away. He has been passed away since I think it's last year. He has been passed away, but he is pretty senior. But he also has made a huge contribution to the Taiwanese semiconductor industry. He actually nurtured several first PhD in Taiwan, and then he also have lots of the industry and academic contribution to Taiwan. And later, since 1960, that people start to understand that it's difficult to have every kind of the semiconductor technology all in the one semiconductor company. So that's why they start to decide that certain of the testing can be outsourced. So since 1960, we start to have this outsourcing of the assembling test. So because of the semiconductor company is way too professional, so you have to be very professional into one kind of area. So they decided to divide the whole semiconductor trend with several different kind of the segment, and then they can start to outsource of the several segment, and then being the certain professional to take care of that segment. So the first one is talk about the assembling testing. As you know, if you've been in Taiwan or the whole, you have been familiar with semiconductor supply chain, then you understand that assembling testing now is also very important, not only for the semiconductor design, manufacturing, but later the assembling and testing. That's also plays a crucial inside the whole semiconductor suppliers. And later in the 1970s, we start to have the concept of a microprocessor. So finally, I think right now several famous names that come to our mind, because the previous actually still have a lot of very famous company, but lots of company has been merged, acquired, or sometimes not exist as more. But I think it's no doubt that starting from 1970, the Intel has in the leading position to produce a very advanced microprocessor. That's also exactly to fit the trend of the personal computing. That's why we need to have this microprocessor. So this is a huge breakthrough, not only in the semiconductor, but also for the technology industry. And later, after 1970, we start have the concept what we call the VLSI system. So that means we can start to integrate lots of the different components, making the very complicated chips in the very small scale. That's what we call the very large system integration, very VLSI system. And this is a moment that the start. We are seeing the trend of the increased trend of getting more and more fabless company. And then because of this dedicated design for VLSI system, therefore there's also people start to get more and more focus on the IP and design tools. So nowadays, why we have so many design tools, EDA tools, is because we need to have the very professional tool allows to do the dedicated design. And also that we're talking about the semiconductor industry, the last one, which is also that's very important, because right now, if you back to the 20 years ago, probably people don't believe it, but at this moment, it's pretty convinced that the new business model, that's what we call the dedicated foundries. Dedicated foundry, that was start from 1985. That was for sure that's the most important contribution from the Dr. Morris Chang, because of his vision with this business model that's called the dedicated foundry. That's why that the semiconductor goes in the certain way that the beyond the human's expectation. So actually, if you look at the whole, these 10 most important innovation, most of them focus on the technology. Most of them focus on the methodology. For example, you have the VLSI, this kind of the mindset. You have the transistor. You have a microprocessor. That's many innovation in the case of the technology. But the only one and very unique. But now in the end, it's become the one to keep booming this whole semiconductor economics is the very novel business model that's called the dedicated foundry. Because of this very breakthrough in the business model, that's why the semiconductor industry is moving in the way that beyond the people expectations. So I think that's good to know that what we already have in the several decades since very early time so far, that what would be the previous genius, previous master, what have been contribute to the whole semiconductor industry. Okay, so then we still have to back to some of the very old technology to understand that the status that state by state until right now. So the first one is that this is the first integrated circuit. Although this is look like just a piece of a little bit mess here, but that's already as a masterpiece is that captured for this is the historical moment when humans first to miniaturize an entire circuit. So we try to make the lots of a component inside of this piece of material. So this is invented by the Jack Kilby in the 1958 in the Texas Instrument. So this is the first time that we have the complete circuit was built on the single chip. So before the IC, the circuit was hand wired using the separate part transistor resistor. But the Kilby's breakthrough is combine all components on one material. That's what we call the integrated circuit. So you can see the idea actually is not that difficult to understand. Just we try to put everything in the one piece of material. But this simple idea is no doubt that completely changed the whole semiconductor technology development. So that's what we have for so far. We just try to make so many different components in the so small tiny chip. So that's what we call the IC. And as we say that the Moore's law is also very crucial, so we also have to explain a little bit more about the Moore's law. So Moore's law means that the number of transistors of the computer chip roughly doubles every 2 years. So that means the density is actually double every 2 years. So more transistor they are, that means that the more powerful the chips become. So the idea is that we just want to, with one fixed space, that we want to put more and more chips inside. Imagine just like if at one certain construction site for the certain building, you know that usually when we try to build out the skyrocketing building, we will have this constructing site, and the inside constructing site is a fixed space. But if we can put more and more workers in the same constructing site, for sure we expect the efficiency can be highly improved. That's the same ideas for the Moore's law. So if we can have this more and more chips, but with a fixed small tiny chips inside, then that means we can produce more high performance results here. So which means that if we have a more powerful the chips, means that the computer and smartphone run faster and can do more. So this is an idea that proposed by the Gordon Morse, that this is law. This is empirical law. That means that it's based on his pure observation in the past, and then he made this prediction. So this is from his personal experience, personal observation, and he did this kind of prediction for the futures. And then he's later as a co-founder of Intel, and then because this law is proposed by Dr. Gordon Moore, that's why that we call this as Moore's law. And this law helps us to understand why technology has advanced so rapidly our day. So imagine that if we have one computer used to take up an entire room, but now in the small smartphone, now we have 100 times of more powerful than those early machines, because right now we have more chips, but with using the small space, right? Because that's why we can insert so many chips inside our smartphone, and that's why we have very powerful technologies here. So that's ideas that how the Moore's law implication to the technology advancements here. So allow more and more transistors be able to be packed in the smaller and smaller chips here. So that's the why the Moore's law is very important. It's very crucial, and the Moore's law was used for the prediction for the transistor density that was already happened in the last 50 years, and then it was very accurate, predict over the past of 50 years. And you can see from this is this solid line is double every 2 years, and this blue dot is a transistor count. So you can see that actually the Moore's law is very precisely to make the successful prediction in the last 50 years. But of course, although the past we can make it, but we are not sure that future we can still make it or not. So that's always a question mark that whether Moore's law will be dead or not. But of course, that we try to have more and more innovation in the semiconductor technology that make sure that we are able to make it follow the Moore's law. So if you look at the past industry, that how the semiconductor technology keep advancing. So basically we can divide by the two main directions. The first one from the 2005 to roughly 2012, 2013, that's what we used to apply the strategy. That's what we call the equilibrium scaling. So the equilibrium scaling, including several innovations that we try to have. That's, for example, the high K metal gate and also the strand silicon. So in the area of this equilibrium scaling, we try to make our transistor scale down with a certain what we call the EOT, that the affected oxide thickness, or with a certain of the matrix. That's what we call as the equilibrium scaling. So use a strand silicon and high K metal gate to increase the speed and also reduce the power consumption. One of the key bottleneck for semiconductor is that, as I already said, that our idea is we try to pack more and more chips inside one fixed space. For example, in this room, we want to have more and more semiconductor chip. But on the other hand, we have to make sure that the overall power consumption is reduced. So that's very difficult because we're getting more and more chips here. But we also hope the power consumption is reduced, because if the power consumption is increased like the density, then we won't have enough electricity to supply our transistor. So similarly, just imagine that let's use the workers example. If we want to have more workers in this room, but in the end we also hope that the overall the food supply for the worker is reduced. So that's very difficult because we're getting more and more people, but the food supply need to be reduced. Otherwise, we will run out of food. So that's exactly same thing that for the semiconductor. We are not only hope for the increased density, but also very important is to reduce power consumptions here. And beyond the equilibrium scaling, after a certain while, we realize that the equilibrium scaling is not enough, that we can make our semiconductor technology follow the Moore's law. So we have to come out with certain new ideas. So we have the new transistor structure, and also we need to have new materials. So in here, we are trying to have a lot of innovation that in the semiconductor, try to make sure that we can follow the Moore's law. So we have the FinFET, which is a new structure. We have the EUV. That's a new advanced lithography. We have the high mobility channel. And we have the DTCO, which is also we need to have the very well collaboration between the design and technology. So all these innovation to make sure that we can start to follow the Moore's law. But at the meantime, we also have to reduce the power consumption here. So as I mentioned here, we have the FinFET, which is a 3D fin-like structure for better control and the energy efficiency. So later we will also talk a brief about the FinFET, because right now the most of the advanced transistor that you use in your smartphone is still mainly based on the FinFET technology. And we have this EUV lithography, so we can make our transistor very small. Because of this EUV can have very small dimension capabilities. And also we start to use high mobility channel, but also it's important for the design technology optimization. So for right now, not only for designer or the technology development, we have to both to understand the design, but also have to understand the process, has to understand the transistor, because in the end, these all will all influence our overall performance. That's why the DTCO is also another very key strategy to keep it advance our semiconductor technology. So for future trend, that's also as already mentioned that this is where we are. We are at the 2025 here. That's already in the age of the N2, N2P. That's in the timing of the production of the N2, N2P. But in the future, beyond the 2030, as I already mentioned, that we are targeting to have more than 1 trillion transistors. So actually the increase of the transistor density is expected to reach to the 1 trillion up to 2030. So now, as a short summary, what we have been mentioned, that you can imagine that a chip as a factory, and then each transistor as a worker. So our goal is try to pack more workers into a small space. But at the meantime, we want to making them work faster, also more efficient. Faster, efficient, but also, which is very important, using less power. So that's our goal. So we want to have more transistor we want to make sure that they are be able to work faster, more efficient, but also that these transistors actually will use less powers. Okay, so that's the how did we make it from the past to keep advancing. Of course, in the future, how do we make for the 1 trillion transistor this is not determined yet. We still don't know. Of course, there are several technologies already proving that's very effective to continue to increase the density, but still we need more and more innovation in this field. And let's back to the even more early time to look at what actually the evolution of the microelectronics. If back to the beginning of the 19th century till the 1950s, that's a half century. In the case of this early half century, that we are still mainly used as a Huawei technology called the vacuum tubes. Nowadays, you can still see some vacuum tubes in some very old machine, but it's very popular in the early TVs, radio, and radar system. We use vacuum tubes, but the problem for vacuum tubes is we need a lot of space. Actually, the vacuum tube cannot be scaled down. Actually, it's quite need a lot of space to storage these vacuum tubes here. And since 1947, we start to have another one called the bipolar transistor. This is 1947 until 1980s. That's we mainly use this bipolar transistor. That's the beginning of the modern chip technology. But nowadays we still use bipolar, but just not popular like before. But for some niche application, we still need to use a bipolar transistor. But since 1960, we have another one called the MOSFET, which is start to dominating the whole semiconductor technology. Not 100%, but probably at least 18%, 60, 70%. That's many use MOSFET. Of course, there are so many variants for the MOSFET. So, but as long as the transistor where we have a metal dielectric semiconductor, that generally can be considered as in the category of the MOSFET. So since 1960, we have the MOSFET, and later we demonstrate that this is a technology that we can make it small, faster, and also the energy efficient, and that's become this as a foundation for all modern computer and smartphone chips with tens of billions of MOSFET in a single chip technology. But as I say that it doesn't mean that we don't need other semiconductor other device architecture anymore. We still need it, but the MOSFET will be around like 70% or 80%. But inside the MOSFET, there are so many variants. So actually, there are many different details in the MOSFET. Okay, so let's start to look at some real experimental result and real electrical characteristics for this evolution of microelectronics. So the first one is we will start to look at this is in the case of the equilibrium scaling, what we actually consider as a strength silicon, germanium channel, and 3-phi material. And the purpose is that because we want to have a mobility improvement. Since we have a mobility improvement, that means that in the end we can have the on-state current increase. So our goal is first, we want to make sure our transistor can have the higher output current. And if you have followed the electronics, the basic electronics in the undergraduate, so you should roughly have a certain ideas about what would be the typical current equation. So if you look at the typical current equation in the transistor in the one MOSFET, which is the saturation current is proportional to the half times mobility times Cx times VGS VTH square. So from this equation, it's very clearly that if we want to increase our output current, for sure that the first things we should do is a mobility increase. So it's not that difficult to understand the motivation. So the overall goal is that we want to increase the current, but that means that we have to do something. And then the first strategy is we try to increase the mobility here. And therefore, we use the strand silicon, germanium, 3-5 channel here. And these are all the topics that people spend more than 10 years finally become the realistic of the product. And later, we start to think about that we start to face several other issues that also drive us to the other considerations. So another issue is that as you know that our goal is trying to make everything smaller, and then in the semiconductor world we call the scaling, so scale down. So we call it scaling. So the scaling means that we want to make the dimension in the one transistor become smaller and smaller. That's what we call the scaling. So if you look at the conventional transistor, where as already mentioned, as already drawn in the first class, that we usually use a MOSFET as an example. So if you look at the MOSFET, that's where we have the source and drain in the left and right hand side, but also on top of the substrate silicon we have the dielectric, and then on top of the dielectric we have the gate metal. So that's a typical case for the transistor. But this transistor, this MOSFET features one characteristic because of this is a place where we call as a channel, and because of the channel was relatively large, so that's why this is a transistor. We have the long channel. So in the case of long channel, everything is fine. That we have the source means that the source is the origin of the electron. So we have the lots of electrons in the source side, and then nothing happens if we don't give any bias. For sure, the electron will stay their original place, and we don't have the current, and we don't have to worry about everything. But the problem is that once we consider scaling, if we try to make our transistor become smaller and smaller, then we start to see the issues. The smaller means that we will try to make our channel small. So still the same, we have a source, we have a drain, we have a dielectric. On top of dielectric, we have a gate metal. So we have a dielectric here. But now our channel is become small, and sometimes very small. So therefore, this MOSFET feature as another name that we call the short channel. And then if you look at, again, the electrons originally will stay in in the source. But now because of this is our electrons. But now because of the channel become so small, and then you can imagine this is a certain wall, certain barrier. And then if you still remember last week, we also mentioned a very brief for the quantum mechanics and for the quantum tunneling. Although last time we mentioned it's very in a brief way, but I think that's enough to help us to understand the semiconductor. As I say, if we move into the very, very small scale, then we have to apply the quantum mechanics. And in the case of quantum mechanics, there's one very famous phenomenon that we call the quantum tunneling. The quantum tunneling means that even this is a barrier, this is a wall, but the electrons can still be able to tunnel through from the source to the drain side, even we don't apply any bias. And that's becomes the issue, because once we have the quantum tunneling from the source to drain, that will cause our transistor have a high leakage current. So therefore, if you try to compare the typical characteristic between the drain versus the gate current, and in lots of cases, we are not only interested in the linear scale, but also the log scale. So therefore, we have to plot the log drain current versus the gate voltage. In the case of a long channel, the transistor is pretty good that in the beginning we have very low current because of our channel didn't turn on, the electron cannot tunnel. So therefore we have the current in the range of the 10 to minus 12. And then this is the moment for our threshold voltage. It's roughly around here. So this is our VTH. So that means beyond VTH, we start to see the current increase, right? So that's a typical IDVG characteristic in the case of a long channel. But nowadays, we're suffering certain issue from the short channel, because right now we have this quantum tunneling can be happen. Even we don't give a bias, even our VG is smaller than threshold voltage. So we can foresee our electron, our current here in the beginning is already high. This probably can be up to 10 to minus 6. And after turn on, the current increase. So this is a case for the short channel. And so now if you try to look closely between the long channel and short channel, the most obvious difference is related to the current here. The current here. And normally this is a current we call as a off current, I off, because of this should be the bias that the device didn't turn on, because we didn't apply enough gate bias to turn on the channel. The VG is smaller than threshold voltage, and therefore the current is should be in the off state. The current should be relatively low, but because of the short channel effect, now our off state current is higher, and thus create another issue is if we try to look at the on off ratio. So this is a place for the on current. This is our on current. So now you can see that in the case of the long channel device, our on current over off is larger. But in the short channel device, our on current over off current is smaller. So that means our on off ratio is decreased. And why I have to mention the on-off current? Because the next slide, we're going to talk about the evolution of microelectronics. In the beginning, was trying to improve on current. We make a certain high mobility channel. We do the strength silicon. But in the next phase, what we want is to have increased on-off current ratio as well. Because of now we're suffering the high off current. That's why usually what we call this on-off ratio control is what we generally call as electrostatic improvement. That's a real name in the semiconductor world. We call this as electrostatic improvement. Why we call the electrostatic? Because of this quantum tunneling is related to the potential well below in the channel that we cannot easily control. We lose a certain control. That's why that we start to suffer in this tunneling. So that's why the real name is called the electrostatic improvement. But in the short understanding, it's mainly related that we want to find a way to increase ion. But at the meantime, we want to make sure the I-off is decreased. So that's our goal. So therefore, there are several innovations trying to address this issue. The first one is SOI, that's we call the silicon on insulator, because as you know, some part of the current is goes through from the substrate. If you try to back to this schematic, that's something we didn't mention, but it's in reality is some part of electron is goes through from the substrate, and therefore the most straightforward way is we just make this as an insulator. The insulator means that this is a high resistivity, and therefore ideally we can remove the substrate lead current. So that's the idea for the silicon on insulator. And another very important innovation is a FinFET. So later we will talk about what is a FinFET. And then very advanced version, which is a nanowire. So the nanowire is, if you look at this schematic, it's basically like this is a source, this is a drain, and the gate is completely wrap out our channel. That's why we call nanowire. But sometimes we also call this as a gate all around. GAA. So basically, the nanowire or GAA, they are talking about at the same things. Okay, so since we mentioned the FinFET, it's definitely we have to talk about the people who actually proposed the FinFET idea, where is Professor Chen-Ming Hu. And Professor Chen-Ming Hu was a professor in the UC Berkeley, but now is also the chair professor in the NYCU. And then normally we call him as the father of the FinFET for his pioneering work in the advanced transistor, and because of his breakthrough in the FinFET, and then later he also has been awarded for many awards, and then of course the one of the most highest level of award is that he received the national award from the Barack Obama to appreciate his contribution for the advanced semiconductor technology. So what is a FinFET? So fin is actually the ray structure shaped like a fish fin. So you know the fish, right? So the bottom side of the fish, usually you will see there's a fin shape. That's very important for the fish to guide their directions. But we also borrow this term in the transistor because of there's a one ray structure like the fin here. That's we call the FinFET here. And the FET is a name exactly same time like the MOSFET, where the FET means the field effective transistor. So the FET is a basic building block for the modern chip, that no matter for MOSFET, for other FET, but anyhow that we try to have this kind of thin shape and then combine on top of the typical FET structure. So why FinFET is important? Because a traditional flat transistor lose the control as they shrink. The shrink means that we do the scaling. That's a lot of leach current. And the flat means like this one is typically we call as a flat or planar transistor, that we have the source electron here, and once apply the Vg, we apply Vd, and therefore we have the electron inverted in the channel, and because we apply the Vd, so your electron can flow to the drain side and become the drain current. But everything is on the one flat region, and everything is in the one typical planar region. That's why we call the flat transistor or planar transistor. But as I say, the issue for planar is that we lose control for this one, because once we do the scaling, there are lots of quantum tunneling can cause a high leach current here. So in a FinFET structure, the gate wraps around the channel on three sides. So you can see this is a FinFET. The main difference is that now we have this source drain as a vertical, and then the gap is wrap the channel in the three sides. So we have the top side and then two side walls, and this gives us a better control, right? Because now you can control the electron here, not only from the top, but also from side wall here and here. So that's why this gives us a better control capability here, and that's enable for the fast, stable, and more power efficient. So ideally, just for the very short conclusion, actually the FinFET is just like a 3D version of the faucet. So allow precise control in the compact space. That's a main difference between the FinFET and planar FET here. And this is a key technology nowadays we use in the very advanced semiconductor advanced application that use this very advanced semiconductor technology. So this is a short summary slide, but if you look at the original paper where he published in 1999, which is the first paper demonstrate for the FinFET, that happening in the 1999 that his group first to propose this idea in the end to fabricate the first FinFET. And this FinFET was demonstrated on the P MOSFET. So this is a P MOSFET, so that's why you see the curve is in the reverse way of the NMOS. But still you will see the several key characteristics is the same, the one we are interested in. We are interested in for the IDVG, right? So in his first demonstration, the most important is showing that the ID and VG characteristic, and then outside he uses a 2.7 nanometer, and most important to demonstrate the roughly 7 millivolt per decade for the substantial swing. And then the SS is actually related to the slope in this region. That's what we call the SS. Later we will talk about this. Is what the full name is called the substantial swing. Or if you follow the semiconductor physics and device, you should learn about some more fundamental related to SS. But in anyhow, the SS is a very key figure because it also indicated that how fast your current can ramp up. So ideally we want to have the curve like in this way, right? If the current can be increased vertically, that would be the best idea we want. But of course it's difficult. So what we want is make this sloper, this increased trend as steeper as possible. Sometimes if you fabricate a poor transistor, you will see your SS is like in this, your increased slope is like in this way. That's something that we don't want. So we want to make this increasing of current as steeper as possible to evaluate this increasing performance. That's why we use this SS as one indicator. Of course, the FinFET has been already in the production and commercialized for I think it's more than 10 years. Of course, we are still improving. There are many ways to improve the FinFET, but as being the academics or being for your research work, we are looking what else beyond the FinFET. That can be something that haven't been commercialized and products, but it's already have the potential to replace the FinFET. So we have to also understand what actually the options beyond the FinFET. And if you look at C, this is a matrix that we have so many innovation in the pipeline that still waiting for us. And then that can be category with a different consideration. We have the conventional, we have a novel, that's based on different mechanism. We have a charge base, we have a non-charge base. So we will quickly go through, and then but each one it takes like more than 20 years study. Sometimes after 20 years study, we realize that this is not the technology that have no hope. But sometimes after 20 years study, we start feel like we still need some effort. This is still very promising, but it just needs some more efforts. So the first one is still related to the CMOS scaling. That's a pretty fitted what we typical understanding for the trend for the semiconductor is we want to do the scaling down. So scaling electrostatic drive and try to minimize the parasitics here. And there are several terms that we have been mentioned. For example, the FinFET, the SOI, but now we also have this gate-all-around. But the gate-all-around can be divided by two different aspects. The one is the edge. It means horizontal gate-all-around, and the one with a V is a vertical gate-all-around. So these are the something that being developed, and then it still feel very promising. And some else is beyond the development, but it's very worth studying, but sometimes still have a lot of pros and cons, and also still face a lot of manufacturing capability, because of when we consider the semiconductor in the product, we are not only consider the performance, because performance is not always the key figure, but sometimes we have to consider, as already mentioned, reliability, but also the manufacturing capability, because we are not fabricating only one transistor. We are fabricating on the whole 12-inch wafer. There are thousands, trillions, lots of transistors we are fabricate day and night, and then therefore the manufacturing capability is also the one challenge here. And in this new mechanism, new switching mechanism, and beyond semiconductor material, for example, the very famous one is this one. That's we call the T-FET, and then the full name is a tunneling FET. And in here we won't talk too much in detail because it's very complicated, and it has been studied for 20 years. It's very difficult to use even one class to explain details. So just let you know that there are many innovations here. So tunneling FET is very promising. Also, we have this one that we call the native capacitance FET. So the native capacitance FET is mainly enabled by the one very attractive material that we call the ferroelectric. So this is mainly based on the ferroelectric dielectric, and then possibly to induce this negative capacitance effect, and then we can produce very high performance chip. And also the 2D materials, that's also very important, because the 2D material has a very unique properties. And some of them is beyond the conventional charge switching, and maybe dramatically different from the CMOS logic. And of course, there are many technology in this segment. Just name few for your general understanding. So, for example, the quantum computing, that's always a buzzword that we heard about every day. And then we also have this all spin logic, spin FET, that's mainly based on the magnetic materials. That's possible to have this kind of spin electronics. In there we can have the spin logic and spin FET. So the overall goal, as I say, that we are not only working make a transistor smaller, but also we have to make sure that we can have the low power consumption. But how do we make us a low power consumption? The idea is that if you look at the IDVG characteristic, and in here, if you try to plot with a log drain current, then the original IDVG in the log scale can be approximately drawn in this way. And then usually we will define as one place as our VDD, where is the operating voltage. So that's our VDD. So low power consumption, that means that we want to reduce the VDD further and further. So if we want to reduce VDD, then actually we should start to produce the transistor where has this kind of a characteristic. if we have a transistor has this kind of characteristic, that means we can have the higher or even compatible drain current here. But now our VDD is reduced. Right, so that's a goal. So now we can see that our goal is trying to have this VDD reduction, because VDD reduction means a lower power consumption. At the meantime, we want to reduce our off current. And furthermore, we want to further and further to have this transistor like in this way. And then again, we can further reduce VDD. And then normally what we target here is our operation voltage for VDD should be below 0.5 volt here. So this can give us the same outputting current, but we actually can reduce our power, reduce our bias, and reduce our bias means that reduce the power in the end. And this is our target. And to make sure that we can reach this target, actually, normally what we have to consider is that we want to have the transistor that can have this slope as steeper as possible, right? If we can make this increase current as steeper as possible, so then we can further reduce our operating voltage. So now, in the end, the goal is to, if we want to have a low power consumption transistor, actually, what our technology spec is, we want to have the transistor where this slope as steeper as possible. And this is exactly where I have mentioned the slope. The real name for this slope is what we call the subthreshold slope. So that's why you will see that many literature, many paper, many technology demonstration, they prefer to show the number of the SS, because the number of SS is one very important indicator here. Just like the previous FinFET pattern, they also show the SS. If you look at the very advanced, the paper from TSMC or Intel, they also show the SS, because the SS is the key to have a low power consumption. Okay, so as we know that the Moore's law is one golden rule, so actually we are trying to have the technology to follow the Moore's law, and sometimes beyond Moore's law, that we can devise two different semiconductor technology trends. The first one is what we call More. So the More is basic idea that we are doing the scaling. So we can see starting from 130 nanometer and down to 22 and so on. So then the goal is to do the scaling. We try to scale down in every dimension, make our chip as smaller as possible. So now we have the 3, and we have the 2, and beyond 2. So that's a typical in the category that we call more. But however, there's another domain that we really didn't care a lot of the scaling, but we more care about the interactions with the people and environment. So this is a technology that we are mainly interacting with the people and environment, and this is a technology we call in the case of more than more. So in the case of more than more, there are many technologies. For example, the analog RF, the passive, the power, the sensor, and the biochips. These are the technologies that we didn't really need to do the scaling. We won't face the issue that whether Moore's law will be dead or not. But we are mainly consider that whether this technology can have more and better interaction with the people and environment. So let's just look at some of the example here. So one of the example is shown as previously you already see that the high V power is one of the category. As I mentioned here, there's also have the high V and power, which is in the range of the more than more, and therefore the one of the important application for high V and power is not related to we have to develop the scaling technology for the power high V, but it's mainly try to have this technology to fit our application. And the recent very important application is definitely related to the AI data center that you have been seeing in the previous slide, that the AI is the driven for the next wave of semiconductor. But due to the AI data center, we also need to have very high efficient power conversion, because the AI data center is very hungry for the electricity. So we need to have very high efficient power conversion. So then this is a schematic for the power conversion from the beginning of the electrical grid down to our GPU. This is our GPU. So now you can see that the electricity from the grid to GPU has to be processed in the many different stages of the electrical converting. So first one, we have this. Normally we have the AC. So we have to do the first stage of the AC convert to DC. That's normally the circuit we call the power factor correction, PFC. Later we have this around 400 or 300 DC. Then we will convert to the low voltage 48 volt DC. And in here we normally have the circuit that we call as a LLC. And later we have this 48 volt DC convert to the GPU, where we only need 1 volt, because this is a low power consumption technology, right? So as I already mentioned, that the inside GPU is the most advanced technology, where the operating voltage is only require 1 volt and less than 1 volt. So in the end, this input is 1 volt. This one is 1 volt. So therefore, we also need the technology to be able to convert 48 volt to 1 volt. But unfortunately, each power converting, we will lose a certain energy, because the efficiency is not always perfect. It's always 95%, 90%. So what we actually want to do is try to have a new technology to increase the efficiency. So one of the example here is gallium nitride. can reach for 98% because due to the certain very good material property, electrical results here, electrical characteristic. Or we can do this as a one stage from 48 volt to 1 volt. Typically in the silicon, we need to have a 48 volt to 12 volt, 12 volt to 5 volt, 5 volt to 1 volt. But as you know, each stage will lose certain energy. So if we can come out using a certain semiconductor that help us to increase efficiency, that will be perfect for our application. So this is one example in the high voltage power. This is a technology that align with more than more. And here is some more recent news that not only the gallium nitride but also silicon carbide, this wide bandgap material is very important for this what we call the 800 volt AI data center. But of course, this data center is not the power that you will use or you will touch every day. But the next one is some technology that you might start to have a little bit a feeling, because this electrical vehicle, the EV car, we also need to have very high efficient power converting, especially relating to this traction inverter, where we are trying to convert the DC become the AC, and once we have AC, we can drive our wheels and make our EV car moving. So this traction inverter needs a very high power, and that's why we also need to have a new semiconductor technology that allow us to improve this energy conversion. And then also that's important to have this higher efficiency. And then higher efficiency means that we can have less space. We can use a smaller space for this semiconductor, so we can make our EV car more compact, more light, and then we can save some weight, and then we can drive in for more distance. So that's an example for this more than more technology. So in anyhow, the power is always a key driving force. It's always a key driving force for our next generation semiconductor innovation, especially for the energy efficient electronics, no matter for low power or efficient power converting and so on, that the energy consumption is always one very important issue. If you imagine that if you can have the 10% energy efficient improvement, that means that ideally you need to make that as a 10 nuclear powers plant for your semiconductor technology. Now you only need to have 9. So if you put it in the large scale, actually the contribution is very important. Originally you need to have a 10 nuclear power plants to supply all of the electricity we need for semiconductor. But if you have a 10% energy efficient improvement, then you only need to make the 9 nuclear power plant. And then you know the difference between the 10 and 9 is not only meaning of a 1 nuclear power plant difference. It also means lots of investment, lots of maintenance, and also lots of safety issues. Okay, so we will take a short break here, and then we'll come back at 11. Yes.
I already sent you a mail.
Did you join the first class?
Sure, yes.
Yeah, but if you don't receive the email for the enrollment, that means you are not selected.
Yes, but I already attended the first class, but the problem is as I mentioned in my mail, it's already registered.
No, you have to, yes, the student will be selected in the enrollment.
Yes,
it's
I
not like
understand.
whatever you put in there, so it's based on the Google Sheet, the Google reply. So I only reply to there's 20 students who are being selected, yes.
But I don't know this about Google Sheet because the class was crowded and we were outside the class.
Yes, I cannot say see, because it's rule. Yeah.
Yes, I
because,
understand it's rule. But I went to the MIRC office, okay, and I explained what's happened during this because I thought that I already enrolled in this class.
No, you don't.
But I didn't, and it's already clear the next day. So they told me that I have to.
Yeah, but our student, this class is full at this moment, so we cannot allow more and more. So you still have to follow the rules. I'm sorry about that. Yeah. But you are welcome to audit this class if you are interested. But I cannot allow more. Yeah,
Cannot.
because now it's already more than 60. You know, the classroom with this size is difficult to allow more. And also for me, it's difficult to make the later arrangement because we have a different teaching activity assigned. Yeah.
Okay.
Yeah, I'm sorry about that.
No.
Yeah, but you are also welcome to audit this class. If you're still interested, just
Actually,
write me email and I will allow you to access Facebook and then you can still access the lecture.
Yeah. Actually, I don't have another chance to attend this class because this is my last semester. So if there's, I know rules are rules, but sometimes the rules
because
does have
many
exceptions.
we also have the many students who are in third or second or third year cannot enroll in this class. Yeah, because it's there are too many students.
I understand this
Yeah,
class is
yeah.
famous. I understand.
Yeah, thank you for interest. And
yeah,
then
yeah.
you can still come. You can audit this class, and then you can still access the lecture materials,
Okay.
access lecture videos, and you still feel free to join this one.
No problem. Thank you.
Thank you. Thank you.
So the second question. So can you intend to have this course in the next semester?
Next one will be the 1 year later. Yeah. We only have this class once per year. You are still can, if you are interested, you can write me email. I can allow you to access all the videos, materials.
I have sent one request in the Facebook.
Oh, but you have to write me email because there are too many requests. I don't know whom by whom, so it's better you write me email. Yes. Okay.
Thank you.
Actually, also this is the first lecture, but since my research is involved in reliability and software electrics, I actually want to do the course. You have answered all the questions.
Yeah, I'm sorry. That's because of.
Can I audit the course?
Yeah. Audio is definitely no problem. So you're welcome. Definitely welcome.
So I will write an email to you.
Yeah. Then you can still access all the materials, all the videos. Yeah. I appreciate that everyone's interested, but it's just difficult to manage such an amount of it because in the first class we have I think probably like more than 70 students want to enroll, but sorry about that. Okay.
So,
Just write me email. I will allow you to answer.
so is there anything I should mention particularly?
You just mention you just mention your name, your student number, and then department, and then once you request in the Facebook, I will to check the detail and then we'll let you in. But otherwise, I don't know.
Yes.
You are the one. Yeah.
Okay. Thank you. I will do that.
Yes.
I actually enrolled in the course, but I couldn't come last week because I have like a small. So I need to have like a excuse because I didn't come last week.
Did you already sign up?
I already signed up.
Oh, you decided that you don't have. Yeah. You already, but you already enrolled.
I'm already enrolled.
Oh, okay. You are in the list.
Yeah, in the list.
Then fine. We don't check the name list
We don't
last
check
week.
attendance.
Yeah. But probably we're starting from next week. Time to time we check because last week and this week still in the time still people, students joining labs. Yeah. So the attendance is not fixed yet.
Okay.
Yeah.
I missed the class and I missed all the labs. Is it going to be the same as in the video?
No, that I already upload the video, but after every chapter I will upload the notice line.
Okay.
So then you access it, but you join the Facebook.
No, the Facebook.
Then just write me email, then I will give you access, and you will see the lecture, all the recording lecture.
I am an exchange student and I'm not very familiar, but if I have the course in E3, that means I'm enrolled, right?
I think so. Or write me email. Let me know.
Okay.
Let me know your names and student number. I will go to the system to check it.
Okay. Yeah, because I think I am.
Okay. Okay. OK。哎，我讲哪边？
The course from ICST.
OK。
And what about this guy you just let me help?
Yeah, I think the first one that they are asking to register TSI courses because you will take time. But he can start to follow.
I checked the earliest course.
That's still okay. Not next semester. Yeah, it's always faster. So the next month, okay. So asking to register.
Yeah. And we have to register.
Yeah. And what's the next registration? Because there's several new students, but I haven't made a complete decision yet who will work on pursue okay, first to let me know, or after this call, let me know what's the deadline to register for TSI.
I already sent see my name in.
Yeah, because I
so do I need to?
because I add you already.
Yeah, yes. Forgot.
this meeting is like
Yes, yes, because I have to go to Taipei, so the next weekend will be the next Tuesday meeting.
so for this week, how should I
I think you still can. Probably this week I also gonna difficult to find the time to talk to you. So I would suggest that maybe let me think. I will try to write email to you because I think the first few months don't have to be hurrying. Just first to get used to the life here because most important is that you need to understand you finish the document ARC
in the process?
Yeah, and probably we can start getting more and more like the training next week. Yeah, and also to assign some tasks.
Next week?
Yes.
So I'm interested in that.
The first one I need you to do is that I want to, as I say, there's some remaining part from Semiconductor, where it's a single compound.
SIC?
Yeah, SIC for the third quadrant characteristic. So I would suggest that I will write email to Semiconductor and CC to you, and anyhow let me know, or if I can find back those materials, and then you can understand what has been done and what else. And also at the meantime, try to read. Do you have his thesis?
Sorry?
You do have his thesis, and I can send you his thesis as well. And I think
Actually, you also stuck in that one.
yeah. So for SIC for the third quadrant, because we want to do the modeling, this is a part of we hope to have some results soon.
It's not like explain like in brief. Just he explained that 2 days like I talked to him.
Yeah.
So he stuck some SIC part modeling. He stuck.
Yes, that's a third quadrant SIC for the very interesting.
Sensors.
Yeah, exactly. That's very interesting because I see so far.
Other thing is also I have a question like
Sorry? Yeah, bidirectional. Yeah. So first try to look at in these two domains.
Yeah.
Third quadrant silicon carbide and also bidirectional. Try to look at these two survey.
Because that is very interesting topic. I have gone through some of the papers.
Yeah, nobody do the modeling for bidirectional gap.
We can do the reliability analysis.
Yes, and then also I probably let's do it this way. First one, I will try to find the Semiconductor CC and probably I can find some remaining work to do and can look at to understand what's the status so far, and then also look at the bidirectional. Yeah, that's a final.
Do you have to paper for that?
We
Fabricated device or something?
But yes, we have a bidirectional fabricate. One of my students.
We can model
Yeah,
that.
we can model one. Yeah, we have a student doing bidirectional.
Or we can go for the reliability analysis.
Yes, that's
So
exactly.
that is the two domain.
Yeah.
Third is SIC.
Yes, yeah.
So I can like Sumendra had like thesis, so I can ask to directly
Yes.
Sumendra to send me a
Yeah.
thesis. You can send.
Okay.
So can I ask?
Yes. Try to write the email. Try to write the email. Try to write email to me and CC.
Okay. So actually he's in touch with me and
I would be happy to put him in calls. Yeah, if he can help.
after he writes the email and he will be the CC and write about SIC and
Yes. Okay, so let's just try to look up some of the latest advancements from the different company, different institute, and we can understand that where we are now and how do we possibly to have the new future directions. So this is coming from the last year from the TSMC, where their roadmap indicate that their process technology evolution, that where some key terms that we already mentioned, for example, the planar here, and then FinFET here, and then the future will be the narrow sheet, this kind of the technology, and also has some of the lithography advancement from the immersion to the EUV. So that's very nice for us to understand that what would be the future technology that we might start to have in our cell phone, in our laptop, and so on and so on. And this is also some of the summaries that come from the 2019 idea, although it has been a while, but still it's worth to look up. This is also from the TSMC. They try to list that what would be the activity, the option they feel that they will still develop, and then that might have some of the potential. But this is mainly target for the low power logic. So you can see the FinFET still in the production, and beyond FinFET, the nanosheet, nano wire, and even the 2D material. So it's very good for research, but for the development and production, sometimes will take quite long time. And this is one from the roadmap from the proposed by the IMEC. Also several terms that probably you already have a basic idea for the FinFET, different version of FinFET, but also have the gate all around. But beyond gate all around, there's what we call the CFET here. The CFET is also very promising architecture. And then what is a CFET really look like, you can see from next one. So the left hand side is a very conventional FinFET. That's we have the triple gate FinFET. And you have the PMOS and NMOS side by side together, but then still take some space because you have a side by side connecting. So the idea would be better that if we can stake in more and more channel with each other, then that would be give us a possible high performance. So that's why we have this gate all around. But this is vertically stacking. Vertically stacked with a lateral nano sheet. And also beyond this, we have the idea of what we call the fork sheet. FET. And then ultimately will be have this what we call the CFET, where the N and P modes stack on top of each other. That's where we have this CFET. So actually the idea for CFET has been proposed almost like 10 years, but nowadays start to be realized in the very advanced technology. Also, this is a very nice slide to understand that if you try to want to understand what would be different between N3, N5, and N2. So the major difference will be N3 will stay mainly in the case of the FinFET, but beyond N3, the nanosheet will be the key one for the N2. And for the technology roadmap can be divided by the two different categories. Where is a high-end, that's a very high performance application, for example, the AI accelerator, the data center server, or to the another one which is a mainstream. The mainstream can be the mobile consumer interconnect. So then you can see that this is a very nice information to understand that if the future, for example, up to 2026, if you use a different technology and different product, then what would be the technology inside this product? And this is also the very latest information. This is also coming from last year. That's what their aspect from what something else beyond the nanosheet. You can see that the CFET also has been already officially put in their roadmap. And beyond the CFET has a 2D and CNT. That's for the very advanced research so far. And this is some of the demonstration from the CFET where they fabricate and demonstrate in the last year IEDN. So this is a PFET and NFET vertically stacked on top of each other, and they demonstrate a very good performance. And as I say that the substrate swing is a key parameter. So now you can see this is SS. This is SS, so they also show the SS characteristic here. That's for the NFET and PFET, and this is a typical transfer curve for the CMOS inverter here. So that's they first to demonstrate that it's possible to make it as a CFET that use for the very advanced node. And this is also just allow you to have quite the overview that actually what else technology. So we have several key terms here: the FinFET, the CoWoS, 3D RAM, EUV, chip-lead, nanosheet, and then these technologies mainly to meet the application for the AlphaGo, for GPT, Trap GPT, and so on, so on. These are some driving force that in the end we need to use this semiconductor technology to realize. And also it will be interesting to look at some other different company, what's their device roadmap here as another very huge competitor for the TSMC for sure will be Intel. So for the Intel, they first to introduce a FinFET. This is their first FinFET in their 22 nanometer technology, and then later they have this enhanced FinFET, And then later, if you look at so far, they still also consider as what they call the ribbon fat, but actually it's an idea very similar to the nanosheet, but just use a different name. But also, it's very important to feature with a different power supply from the VR. So this is a powering from the VR. It's a very complicated, so I won't mention too many details here, but just let you know that we have been spent lots of efforts, and different companies spend lots of efforts try to have the technology that are able to catch up with Moore's law. Okay, so this is the last slide for these introductions. So now we'll move to the next one, which is start to getting more and more related to reliability. So in the first one, still mainly we talk about the basic related to semiconductor, and then how's the semiconductor developed so far. Okay, so that's in the second chapter, we will talk about the overview of the electronic device and their reliability, and we will start to talk about some of the equations, some of the mechanism inside, and sometimes the contents might be new to you, because I believe this is a content that probably you never heard about from other subject before, but for the first time you learn this, probably it's a little bit difficult to follow up, but if you try to spend some time to understand, it's not that difficult. Okay, so first one, just want to remind that what will be expected to have learning from this chapter. So by the end of the chapter, you should be able to, first, it's important to able to define reliability in the case of what is actually reliability means, and also is able to explain statistical nature. So that's also, I already mentioned in the last slide that the statistic is very key for the reliability analysis, but now we will start to getting more about what else, what actual statistic you have to understand here. So then by the end of this chapter, you should start to digest that when we talk about reliability, the statistics by nature that we need to understand. And then also try to understand the differentiate between the failure mode. We have the several key terms we will introduce. The first one is the failure modes, and then the failure mechanisms. What's the difference between these two? The failure mode is something like the symptom that we observe, but the mechanisms inside the reason that lead to these symptoms here. And then also, there are some key reliability metrics that we will talk about: the NTTF, the NTBF, and then the failure rate. So there's some equation that we will introduce here. And also, you should be able to explain the role of the time, temperature, and stress condition in the device degradation, and you are able to apply reliability concept and then to evaluate device performance and predict lifetime. And then also you should be able to recognize that the physics-based model and then acceleration testing that it's important to ensure the robust device design. So that's some of the learning outcome that you can have the idea that by the end of this chapter, this is something that you should learn, you should be aware of. So the first one, what is the reliability? So reliability as a probability of operating products for a given time period under specific conditions. Without failures. So that's a typical definition for reliability here. So from this definition, we can start to understand the nature of the reliability is very well correlated with several things. The first one, because of the probability, that's why we need to have the only way to analyze the probabilities, we need to have the statistical tools. So that's why the statistics is always a key analyze, key mathematics when we talk about reliability. Because when you talk about reliability, sometimes you have a random value. You test 100 device, you only got a 2%, 10% fail. But how do we analyze this probability? For sure, the statistic now is very important. We need to make a certain distribution. We have to use this distribution to analyze the probability. So that's why statistics is always the key for reliability. And second one is very important is the time and condition. So when we talk about the reliability, it's important to specify this is a condition under how long for your testing. What is the bias for your reliability? Because we cannot say this is product is a perfect reliability, but without giving the details. Because the details, this kind of the time and bias dependency will dramatically change the reliability characteristic. So as I already said last week that we have the very well-known standard. This standard is that every product want to qualify has been passed as what we say the JDEC standard. So inside the JDEC, there's several different testing items. For example, the HTGB, which is full name is a high temperature gate bias. HTGB. And then HTGB, if you try to look at the definition for HTGB, they will tell you that you have to test HTGB at a certain hours. For example, 3,000 hours. And at one condition, especially the bias condition, which can be 150 Celsius degree at the VG 10 volt here. So therefore, the time here, 3,000 hours, is related to the definition of the given time here. And then conditions is also related to the definition where we mention as a one specific conditions. And when we talk about the JDEC, they always mention that you have to try to measure, you have to do this. You cannot, of course, they won't ask you to do every device you are manufacturing. They won't ask you to do every device you are producing. They will just randomly select the several laws. For example, the general standard for the JDEC is 3 laws. And then each loss you have to pick up the 77 device. For each lot. So why we can have a confidence about this sampling is enough, because what you are going to do is you are going to fabricate 100 lots, 10,000 lots. You are going to make the 10,000 wafer, but we only select the 3 lots, and each lot we only have the 77 device to testing, because this is based on the statistics. With some statistics that tell us that this kind of sampling is enough to prove that our product has a good reliability. So if you try to look at this JDEC standard, then you can understand that this standard is very well aligned with the definition of the reliability. And when we talk about probability, sometimes probably you haven't used probability for a while. My last, when after went to the college, to be honest, I really feel to use, I seldom use probability. So the most impressive moment I used probability is when I was high school, because in the college, and even for graduate school, that sometimes that everyone is interested in the different domains. Some domains really heavily rely on the statistic probability. Some domains we don't use probability. So it's still good to just try to remind everyone that what is actually the definition of a probability. So the probability means that the sampling of a product the sampling of product for testing, the statistics analysis. Statistical analysis of value test result and the result use of the distribution function. To describe the population that fail. So that's a basic definition of a probability. So we will only test with several data, right? The sampling means that you have a 100 product, but you won't test 100. Probably you will pick up only 20. So that means a sampling product, and then we will use the statistic for value test result, and then to further project the result, because you only test on the sampling product, but in the end you still want to have a result project on all of the product. Then you need to apply the distribution function. That's why the distribution function is important, because the distribution function can give us a projection from small amount of sampling data to the whole device, whole the product that we are always going to sell to our customers. And also, when we talk about reliability, it's always considers a time dependency characteristic. So the time dependent dependency of a reliability implied by definition is already there's a time inside reliability, and therefore the time variables appears in all of the value distribution function. So that means that we still need to incorporate time factors, variables inside the distribution function as well. And when we talk about the time, then we have to make a little bit clearly definition that in general, when we talk about the electrical result, we can divide by two different what we call the time related. The first one is what we call the time zero. And then the one beyond the time zero is what we call the time dependent. So the time zero usually means that to characterize this device, but with we don't consider time is fresh. So that's why we call the time zero. So it's always considered as initial characteristic, fresh characteristic. That's usually sometimes people call this as a time zero characteristic. But after the time zero, after your fresh characterization, you start to see you characterize for the 100 times, for the 100 hours, and then we start to have the time-dependent characteristic. So, in overall reliability, which is a time-dependent degradation. So, normally we don't see this reliability effect in the beginning, but afterwards we see this reliability effect. So this is the bottom figure is one example. There's some chip inside your personal computing, and then you will try to turning on and turning off trillion of times. So it's very important to understand the lifetime for these the chips as well. And then once we use for longer time, probably beyond 1 month or several years with the timing pass by here, then we will see this kind of instability can be happen, which you try to look inside, which can be the defects. So because of with a time-dependent degradation, that a time-dependent defect generating, we start to have a defect, and because of the defect, you start to have this instability. So that's one example that why our personal computing with the time pass by, in the end the performance is getting poor, and sometimes you cannot turn on anymore. That can be the defect can be generated after the certain of the moment, and in the end cause lots of instability. So one of the very famous reliability mechanism related to the time is what we call the time-dependent dielectric breakdown. To be honest, every reliability are all related to the time, but just a time-dependent dielectric breakdown is just already written on the name. So that's why it's definitely related to the time as well. So the time-dependent dielectric breakdown is a very serious reliability phenomenon in the, no matter for what kind of the technology you are working on, for the advanced CMOS, for the memory, for the even for backend, for the interconnection line, we are also suffering the TDP. In the 3D IC, we suffering TDP as well. In the power device, in the every technology, we always has this time-dependent dielectric breakdown. So first, we have to understand that the typical characteristic for the gate dielectric can be shown in here. We have this IG, VG characteristic, and then normally we will sweep the VG. After a certain moment, we see the increase of a current here, and we define this increase of a current as a breakdown. But of course, you already know that this is a breakdown point. So normally you won't operate this breakdown bias. You will probably try to be safe. You will have the 10 volts below the breakdown, 20 volts below breakdown. So let's look at, if we try to bias at this moment, which is far away from our breakdown. But ideally, our device should be safe because it's far away from breakdown. But in reality, this is not true, because even with bias at low bias region, as the time passes by, as the time is longer enough, we're still suffering this breakdown. So that's why we call this as a time-dependent dielectric breakdown. So in the beginning, if you try to bias at this point, and now we will start to plot the characteristic where our gate current, but now no more the bias, because now we consider fixed bias. What we are interested in is a time factor. So we have to consider the time here. And if you try to plot as a log scale, so no, we will start to find out that in the beginning, the current is very small, which is this one. This is the timing of this one. Because right now, the device is pretty in the good shape, and then we bias in the low voltage. But if you try to look at the inside the dielectric, you will start to observe that the defects might start to gradually generate. So this small square means that the defect. But overall, your current is still low because of you only generate the very limited amount of defect. So it doesn't make the damage of your device, and you won't sense any difference. So your current is low, and you still start to operating your semiconductor device for a while. Then again, up to this region, up to this timing, still the current still quite low. You don't feel anything change. But if you inside the dielectric, you will find out that the defect number is increasing. But overall, still quite small, so you don't feel anything. So you still feel like, yeah, my device, my semiconductor device is still quite good. But I also want one thing to illustrate that ideally, we have a uniform dielectric. Ideally, we apply the uniform electric field across all the dielectric. So the defect generation is random. This defect So we have a random defect generation because of we don't know that which location will come out with defect. And then if you test at 10 devices, probably your defect will be generated with a different location. That's another reason why we have to apply the statistic, because we cannot specifically locate where the defect generated. So anyhow, the defect generation is random. So after a certain while, up to this blue timing, device still quite good, the current is low, and therefore we keep operating our device. But now, at a certain moment, we start find out that there's a moment that will also face a breakdown. And then the reason of this breakdown is because of we getting more and more defects here. But suddenly, there's 3 defects align with each other because of one leakage path. And because these align with this with one line and become the leakage path, and therefore your electrons can start to go through this defect and tunneling through this defect, and then becomes a huge leak current here. So that's why we still suffering the breakdown here. So this is a very short version to explain TDB. Of course, some of the model is very complicated, but these slides already catch around like 70% of the key understanding for the TDB. So let me just illustrate again. In the beginning, you have very few defects. As I said, the defect generating is random. We don't know when or where the defect will be generated. You just come out here, here, here. With the time pass by, you come out more defect here, 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 here. And as the time accumulated enough longer, anyhow, there's always a chance that defect can degenerate that connected with each other and become as a leakage path. And this defect, since it has been aligned with each other, so then the electron can be go through this and become leak current, and then we have this breakdown. And this is leakage path. But in the TDB, we don't call this leakage path because the leakage path is a too general term that has been used in the many different occasions. Therefore, we give a name that we call the percolation path. So in the TDB world, we call this as a percolation path. Once we have a percolation path, we found out our dielectrics immediate breakdown. We have a high gate lead current. So because of this defect generation is randomly, and then the formation of the percolation path is also randomly. So normally we call this as a phenomenon that we call the stochastic. So stochastic means that having a random probability distribution that can be analyzed statistically. But not be possible predict precisely. So this is phenomenon that we call stochastic, which is a random probability distribution that can be only analyzed statistically, not be able to predict precisely. So that's why, again, we need to have the statistic tool. So the TDB is one of the very good example to understand the nature of random for reliability. Of course, for the other reliability issues, the same. We are also suffering the random, but this is a very good one that clearly understand how the physics, the defect formation is kind of the physics-based defect formation, but how this physics can well align with with the probability, with the random nature, and then we need to have the statistic to analyze. So reliability, which is a stochastic process. And terminating by a threshold hole. What it means terminating? That means that this process will be triggered to the breakdown once there's a threshold hole. This is a threshold condition. The threshold condition for this one is that all the defects are aligned with each other, and then suddenly the device are breakdown. Okay, so next one, the specific condition. The specific condition can be relative. You have to clearly define the condition, which can be your bias, your temperature, but sometimes beyond bias temperature, sometimes even the humidity. We also need to take into account, especially in the package level, the humidity will influence our package materials properties. So humidity is also very crucial condition. So we have to specify the product testing or operation conditions. Is essential in predicting reliability. For example, elevating the temperature is a universal way to accelerate the values. Therefore, it will make a big difference whether the test temperature is 25 Celsius degree or 100 Celsius degree. So that's a very important. This is also give us a very good acceleration testing. So what does it mean acceleration testing? Just use a very simple, this is a very common methodology in reliability field that we want to accelerate the whole process. For example, if you have you are going to do the one kind of a technology for reliability testing, and first, of course, we usually starting from the room temperature, which is 25 Celsius degree. But you will find out that if you try to test at the 25 Celsius degree and you only give the bias at the 5 volt, then the device will be failed after 5 years. But 5 years is not a reasonable time for testing. If you test one device after 5 years, found out that this is broken, but how can the 5 years is a pretty longer time, so it's not realistic. There's no company will wait you for 5 years. But how we can shorten this process? That's why we need to have this what we call the accelerating testing. So in the case of acceleration testing, one of the most often strategy, we just heat up our sample. We just do this at a high temperature. For example, we start to test at a 150 Celsius degree. If we do in the 150 Celsius degree, again, we try at the same 5 volt. Because you heat up the sample, you do it in a high temperature, all the reliability, all the degradation mechanism will be accelerated. Then your device will be moving to the much faster in the way of the value. So now you probably will start to see your device will be fail in the 100 seconds. So 100 seconds is a reasonable time that we can manage in the lab, in the testing equipment. So you can test many devices, and each device will only broken in the 1000 seconds. But now we still have to find a way to calculate back to the lifetime in the 25 Celsius degree. So now we will do some calculation. So we need a certain model for lifetime prediction. At the 25 Celsius degree. So this is how we actually doing the lifetime prediction, because in anyhow we cannot test. If you have a one product that you can claim for 10 years lifetime, how can you make it to test for 10 years? This is not realistic testing time. So we will do the acceleration testing that will make our product degrade faster, break down faster, and then in there we need to have a certain model for lifetime prediction. And this model has become very crucial, because this model can be in the end determine where our prediction is successful or not, where our prediction is accurate or not. So then this model normally is involved for the physics-based understanding with some very nice mathematics analysis. So that's why the physics insight is important, because if we can understand physics, we understand what kind of the mechanism that drive for the device degradation, we can use this physics-based model to predict the lifetime. So similarly, other specification might be voltage, humidity during the testing of use. And also we have to understand that when we talk about value, there's several different levels of value. We have to be clearly about the values. So the question of what is meant by value must be clearly addressed. When we talk about value, does it mean the actual value of breakage? Of a component. So when we talk about the value, what it means is it's an actual fracture. Actual fracture of breakage, or this just means a certain degree of the performance degradation. And if so, how much? So normally, when we talk about degradation, could be, for example, you have a VTH shift around 50 millivolt, or you have R change around 20%. So these are typical degree of performance degradations here. So that's we also need to define that this can be the failure criteria. It doesn't have to be the actual breakdown. It can be that you have certain performance has been shipped up to a certain criteria, then we can call this as a degradation or value as well. Does it also mean that a spec is not being met, and then what is actually the spec here? So Despite these uncertainties, it's generally accepted that product failure occurs when the required function is not being performed. But in our analysis here, we very often to define the value where we consider the certain level of the degradation that degradation has already achieved. For example, our threshold voltage shift to certain value, for example 50 millivolt, or on resistance degrade for a certain percentage, then we consider this is a value. So we very seldom to consider the actual breakdown, because of that's not realistic. Sometimes before the breakdown, your typical characteristic has been dramatically changed, and sometimes the overall performance already poor enough. It's not really functional. So normally we will consider some degree of performance degradation as a value, and therefore the definition of the value is become the critical here. And a key quantitative measure of reliability is a failure rate. And this is a rate at which a device or component can be expected to fail under some known conditions here. So the failure rate is very important. That gives us a good way to predict. For example, if you do certain analysis, you already know that your failure rate is a 1% increase per week. Then you can know that if you set the spec, the reliability value is a 20% increase, then you consider as a fail. So that means after 20 weeks, you cannot use the device anymore. So then we can make the simple estimation that 20 weeks of lifetime. That can to reach for 20%. So that's why the failure rate is useful for us, because in the end we can use the failure rate to predict the lifetime. Of course, in reality, the failure rate will not increase linearly like just in this case. Sometimes it's a very complicated equation, but this is a very simple example that everyone can understand. That if we can determine the failure rate, that means we can determine the lifetime of the product, and also then we can tell our customer that how long you can use our product. Okay, so the next slide will be spend a little bit time to explain the failure physics, what's a failure modes and failure mechanism. So I think we can leave the next slide for the next Monday. So we will stop here, and if you have any question, just feel free to let me know. So we will see each other next week.